Dear students, welcome back. In the previous lecture, we had introduced the method of undetermined coefficient, which was used to find the general solution of linear constant coefficient inhomogeneous ordinary differential equation. In this lecture, we are going to introduce a method for linear variable coefficients ordinary differential equations. Okay, so far we have been seeing constant coefficients, right? So far we have been seeing L, where you had this coefficients to be constants. Now we are going to look at coefficients depending on the independent variable x. Okay, so that is what we will be doing today, and this method is called the method of variation of parameter. We will also introduce a special form of variable coefficient linear ODE, which is the Cauchy-Euler equation, which can also be solved in a special way by some change of variable. Okay, that will be the content of this topic. This lecture. Okay, so the method of undetermined coefficients was to find the particular integral for, as we have seen, for some restricted class of constant coefficients linear ODE, right, where you had Ly equal to f, where this L was constant coefficients differential operator, and this f was special cases like e power x, or polynomials x power n, or the trigonometric polynomials sine and cos, right? In fact, you can have sine ax plus b and cos ax plus b and so on. Okay, so this could be m and so on. So this is a type of f that we have used the method of undetermined coefficients, right? So in this lecture, we are going to introduce a technique which will work for variable coefficients. That is, instead of constant coefficients, you will have variable coefficients, okay, of this form, and we will and the same technique will also work for f much more, for other classes of functions as well, and not necessarily restricted to this class of functions, which is called the method of variation of parameters. Okay, like whatever we had introduced in the previous lecture, even for constant coefficients, right? Even for constant coefficient, for this is a constant coefficient ODE, whereas if you take fx to be tan x, this is a trigonometric function. Okay, this is a trigonometric function, but still the method of undetermined coefficient will not work for this ODE. You cannot apply it to this ODE. Okay, whereas the method that we will introduce in this lecture can be used to tackle this kind of differential equations, where you have the right hand side different from the cases which we have discussed in the previous lecture. And the name of the method is what is called the method of variation of parameters. So like the method of undetermined coefficients, even for variation of parameters method, you should be able to compute the complementary function, right? Even for the previous method here, we were able to compute the complementary function, and then use the undetermined coefficient method to find one particular solution and add it to the complementary function, right? You also do something similar for variation of parameter. You still need complementary functions, and using that you can write down a general solution. We will describe the method. So let's take a second order ODE. let's take a second order ODE of this form, and let's say that you can find its complementary function, which is the linear combination of two solutions y1 and y2, because it's second order, so that it should be a linear combination of two linearly independent functions, which is y1 and y2. So what is the method of variation of parameters? What it says is that now you look for a particular solution, right? So you look for a particular solution as a linear combination of y1 and y2, where now you don't use constants but you use functions of x. So you want to determine so v1 and v2 are unknown functions. So you want to determine v1 and v2, which are functions of x, not right, which are functions of x, not constants. So you want to determine v1 and v2, and once you determine v1 and v2, since y1 and y2 is the linearly independent solution of the null space, then you have the particular solution, and hence you can write down the general solution by adding the particular solution to the complementary function. Okay, so when we say we want a particular solution, what is that we want? We want that this yp is a solution to this second order ODE, right? That's what particular integral means, right? So if we substitute yp in this ODE, it should be satisfied. That is how we should choose v1 and v2. So v1 and v2 has to be chosen such that yp is a solution to this ODE. So let's compute yp prime. You will get an equation like this. Okay. Now if you differentiate this again, yp double prime, in order to substitute here, then you will see that you are going to get a double derivative of v1 and v2, right? When we derivative the terms here, we will be getting double derivative of v1 v2. So to avoid that, what we do is that we impose this condition that this last term is 0. We just impose this condition, right? So we want to choose v1 and v2 such that yp is a particular integral. So in that situation, we also impose an additional condition that v1 and v2 are such that v1 prime y1 and v2 prime y2 is 0, because if we impose this condition, this term vanishes, and what is left is just v1 y1 prime, v2 y2 prime. So you had yp as v1 y1 v2 y2, yp prime is v1 y1 prime, v2 y2 prime. Okay. Now you differentiate. So once you impose this condition, you have this equation. You differentiate this once more, second time. Okay. So yp double prime is equal to v1x y1 double prime x v2x y2 double prime x plus v1 prime y1 prime v2 prime y2. So this is just the derivative of this term here by product rule, right? v1 y1 double prime and y1 prime v1 prime and so on. So this term is coming from the first term and this is coming from the second term. Okay, y2 prime. Now what is the condition? We want yp to be satisfying this ODE. So we need to choose v1 and v2 such that yp is a solution of the ODE. So if you substitute it in the ODE and if you equate, you see, so you substitute it in the ODE and substitute for yp double prime, yp prime and yp and rearrange it as a2, v1 and v2. So you see, so that ODE becomes this. So you have three terms here. You see that this is nothing but y1 satisfying the ODE with the homogeneity condition, right? y1 and y2 were solutions for the homogeneous equation, right? That is how y1 and y2 are chosen, right? So y1 and y2, if you remember, are solutions of this ODE. So this is 0. Similarly, this is the y2. y2 is also a solution of that ODE, so this is also 0. Right, from the fact that y1 and y2 are solution to this ODE. So the second term and third term vanishes. What you are left with is only the first term. Right. So what we have now come down to is that we want to choose v1 and v2. Right. So in this case, I'm just saying that the coefficients of v1 and v2 vanishes. Right. Well, whatever I just explained. So it's the same point. So once we have that, so we want to choose v1 and v2 such that yp is a solution to the ODE, and that can be done. So if yp is solution to ODE, that means this condition has to be satisfied. Plus, you remember the first condition that we had imposed, right, in the previous slide. This condition. So v1 and v2 satisfies two conditions now. And that is what I have written here in the matrix form. So your v1 and v2 should be chosen such that it is solution to this matrix equation here, whatever we have here. Right? The first equation is coming from the first equation we imposed in the previous slide. The second equation is coming from whatever I have highlighted here. Okay, and y1 and y2 is known, so this matrix is known. F is known, a2 is known. So here if you can solve for this matrix equation, then you are done. Right? Can you solve? Yes. So since y1 and y2 are linearly independent, right, we have already seen a result that the Wronskian is non-zero, and Wronskian precisely means the determinant of this is non-zero, right, which means that you can invert it, so you can solve for v1 prime and v2 prime. So v1 prime is precisely this, where w is the Wronskian, and v2 prime is precisely this, where w is the Wronskian. Okay, and if you integrate both sides, you are going to get a formula for v1 and v2. So you have solved for v1 and v2. And once you have solved for v1 and v2, right, you have solved for v1 and v2, you go back, since you solve for v1 and v2, you know what is yp. Since you know what is yp, your general solution is yc plus yp. Okay, so let's look at examples so that you understand better. So let's take the same equation that I said, so you cannot apply the undetermined coefficients method, right? So let's take this constant coefficient second order ODE, where the right hand side is tan x, which is not covered by the method of undetermined coefficients. So its complementary function, you know, is y double prime. I mean, its homogeneous part is this, and this has two linearly independent solutions, which is sine and cos. So the complementary function is a linear combination of sine and cos. Okay, so far it's fine. So now we want to find v1 and v2 so that we can write down the yp, right? We said yp should be v1 sin x plus v2 cos x. Both v1 and v2 are functions of x. And what is the formula for v1 and v2? We have already derived it in the previous slide, right? So v1 prime and v2 prime are solutions of the matrix equation, right? So we had a formula for v1 prime and v2 prime, right? This formula v1 prime and v2 prime, which is precisely minus f y2 a2 w. We just use this formula, right? If we use this formula, we compute that v1 prime is sin x and v2 prime is cos x minus secant x. Okay, so using this, if you integrate, you get v1 as minus cos x plus some constant, and v2 as sin x minus log secant x plus tan x plus some constant. Now, since you want specific, you just choose whatever constant you want, c1 and c2. So use this information v1 in your equation for yp. which is v1x sin x, v2x cos x. So if you use in that information, you get that yp is this, right? v1, which is this, into sin x will give you one term, sin x minus cos x, and v2, which is this, multiplied by cos x. You multiply this by sin x. You see the first term here cancels with the first term here. The second term here is here, okay, and this is here, and what you have here is precisely this. Okay, so this is your particular integral. So your general solution is just the sum of the complementary function and the particular integral. So this is your solution. Okay, so we were able to solve this using method of variation of parameters. Let's look at another example. So take this ODE, second order ODE. Now here you see the coefficients are all variable coefficient, they are not constant, and here you have an f which is anyway, right? You have a f which is non-zero. So what do? You first solve for the homogeneous sorry, you don't solve for homogeneous equation. We have seen this, so we have to find, this is a second order, so we have to find the functions which generate the null space of this. Okay, we don't have any method to deal with variable coefficient even for complementary function, but when we introduced the reduction order method, we had used this example, and we had shown that there are two linearly independent solutions to if there is one linearly independent, so if there is one given solution, then you can find a linearly independent solution to the given solution, right? So in that example we had shown that this for x and x square minus 1 are two linearly independent solutions, and since this is second order, that should span the solution space, so that should span the null space of this problem. Okay, so this is the complementary function from the previous. It's like we have guessed this, right? So someone gave us one solution, and using the one solution and using the reduction order technique, we found another linearly independent solution, and because it's second order, the span should be the full solution space, right? So that's the complementary function. Now to find the particular integral, you use the formula again. You have to find v1 and v2, and v1 prime and v2 prime formula involves the Wronskian. So you compute the Wronskian, which is x squared plus 1. So if you use the formula, you get v1 prime is this and v2 prime is this. Okay, and if you integrate, you get v1 and v2. Now you can choose any arbitrary constant c1, c2, doesn't matter. And now you use this information, so your y, so without loss of generality, or it doesn't matter for any choice. So this is valid for any choice of c1, c2. We just need a particular solution. So to keep things simple, we can choose c1 and c2 to be 0. So in that case, your yp is the sum of, so it's v1 times x and v2 times x square minus 1. That's what we have here. So you get yp to be this, and that if you add it with the complementary function, you get the general solution. Okay, this is method of variation of parameters. Another example, in this case it's a third order constant coefficient ODE. So you see this is again of the form fx equal to e power x, which we can probably do as using the method of undetermined coefficient. So you can try doing that. Only as an example, I am showing it via method of variation of parameters. Okay, so this is a constant coefficient with e power x here. So if you look at the corresponding homogeneous equation, you will get a three degree polynomial right? Cubic equation, which you, if you solve, you get three roots, 1, 2 and 3, which are real distinct roots. So you get your complementary function to be this linear combination of e power x, e power 2x, e power 3x. Okay. Now to find the particular integral, you choose yp to be v1 times ex, v2 times ex, v3 times e3x. So you have three unknowns that you need to find. Okay. So if you do the whatever we had described for second order, if you do the same thing for the third order, you see. So if when we compute yp prime, you will get terms like this, and the other terms we put to be 0. So this is the additional condition that we impose on v1 prime, v2 prime, v3 prime. Now if you compute the second derivative of using this equation here, right, you get this with this condition again, right? Right, with the additional condition that v1 prime x, v2 prime v2x, and 3 v3 prime v3x is 0. Okay, so this is the additional condition. So once you differentiate this, you will get these terms which you impose to be 0. So you have one more. See, for the second order you had so for the second order you had two conditions. Now you are in the third order, so you get one condition from the first derivative, you get another condition from the second derivative. Now when you compute the third derivative, you will get that third condition using the ODE. Okay, so here if you differentiate this, you will get terms depending on v1 prime, v2 prime, v3 prime. You just equate that to 0. That is your additional condition. Okay, so for third order you employ the same technique, but now because it's third order, you will have a matrix equation which involves a 3 cross 3 matrix, right? Which means you need three conditions. So that's what we are obtaining here. One condition coming from the first derivative, and then you get the second condition from the second derivative. Okay. So one condition is here from the first derivative and another condition here from the second derivative. Now you compute the third derivative. Whatever is appearing in the third derivative, you have this. Now you use this third derivative, second derivative, first derivative, and y, everything in the original ODE, equate. Okay, then you get, so we need to choose v1, v2 such that yp is a solution to this. That gives you a third condition. So now you have three conditions. So you have three conditions, three unknowns, v1, v2, v3. Okay. So you get this matrix equation. Those three conditions becomes this matrix equation for the unknown derivatives v1, v2, v3, right? Okay. And now by the linear dependence of this matrix, the Wronskian will be, if you look at the determinant of this matrix, it is non-zero. So it's invertible. So you can actually solve for v1 prime, v2 prime, and v3 prime. It's just the inverse of this matrix. So once you have v1 prime, v2 prime, v3 prime, you have v1, v2 and v3 with some constant c1, c2, c3, which you can choose arbitrarily. So without log of general, we just choose the constants to be 0. So you get a particular integral because you get v1, v2 and v3. Use that with the general solution, right? So your general solution was here, right? This is your, this is your complementary function, sorry. So plus yp, where yp is this, where you substitute for v1, v2, v3. So you see alpha 1 and v1, alpha 2 and v2, alpha 3 and v3 will combine. And that's what has happened here. Alpha 1 and some v1 and alpha 2, alpha 3 has combined. Okay, this is coming from v1 because of the linear, because there is one repeated root, if you notice. Okay, so this is the general solution. Okay. Okay. So with this, I think you would have understood. We have seen enough examples to understand the method of variation of parameters, right? So now let's introduce a special case of a variable coefficient ODE, which is called the Cauchy-Euler equation. Okay, and in this form again you can compute the complementary function easily and so on. Like for instance, the previous example, if you notice, not in the previous, I mean in the one example before this, right? Which one? This one. This was a variable coefficient. Here you just had an already used technique to find the two linearly independent solution. So in general, you don't have a technique for a variable ODEs, even if it's linear, right? Whereas now we have, so for the Cauchy-Euler equation, things become easier. Okay, though they are variable coefficients. So what is a Cauchy-Euler equation? A Cauchy-Euler equation is an ODE of this form, where the L is this form. So the coefficients AIX are appearing as some constant times power of x. This is how they appear. Okay, so whenever your linear ODE is of the form such that the coefficients which depend only on x, right, because only then it's linear, only on x are actually some scalar times some power of x. If the coefficients are of this form, all the coefficients are of this form, then that ODE is said to be a Cauchy-Euler equation. Okay. What is the advantage of this form of ODE is that in this form of ODE, if you use this change of variable, this transformation, so depending on the domain, so if this is in differential equation, then the x is coming from some I, right? So I could be on the positive line or on the negative line, or could intersect and so on, right? So depending on whether x is positive or negative, you can use this transformation. So when x is positive, you plug in, so you introduce this variable s, which is natural log of x. Okay, then more or less natural log of mod x. Okay, so depending on what is x, and so that's what I mean by when I say depending on x. So when you use this change of variable, and if you rewrite this ODE in the s variable, then you get a linear ODE with constant coefficients in the s variable, and you know how to solve a linear ODE with constant coefficients even if it is inhomogeneous, right? You know how to solve it. You either use the method of undetermined coefficients or you use the method of variation of parameters. Okay, that's the advantage of this form of ODE. Let's look at some examples to understand, but before that, let's see what is the proof of this theorem. So what do? You set x equal to e power s, which means you are introducing the new variable s, which is log of x. We have assumed here without loss of generality x is positive. So now what you have to do, you have to rewrite the ODE which is in the x variable in terms of s variable, right? So what is the derivative of y with respect to s variable, which is this, which is xy prime. Similarly, the second derivative of y with respect to the s variable will become this, right? So, or which is equal to this, right? So from here you get this, right? So if you go on like this, more generally you can show that for any kth, if we start computing the kth derivative, you have this relation xk, and the kth derivative of y is this. This you can show in the iterative process, okay, or by induction. Okay, so you have this formula. So in particular, for instance, if you have a second order, if you started with a second order ODE of the Cauchy-Euler form, So how does the second order ODE of the Cauchy-Euler form look like? It looks like a2 x square d square y by dx square plus a1 x dy by dx plus a0 y equal to fx. Right? Now if you replace, so where you have d square by dx square, where you have x square d square y by dx square, you use this formula. Where you have x dy by dx, you use this formula, x dy by dx you use this formula, right? And wherever you have y, right, y will remain of course y, and wherever you have x, you replace by e power s. So then your ODE, which was originally in x and y variable, will now become an ODE in s and y variable. Okay. Similarly, if you are higher order ODE, you can use the formula which we have said here to compute. So in this way, you can transform the Cauchy-Euler ODE into a linear constant coefficient ODE in the s variable. Okay. So that's a proof of that theorem. So let's look at some examples to understand these things. So you see this is a Cauchy-Euler ODE. Why? Because it's x square y double prime. So it's here a2 is 1, right? Plus or minus 2x. So here a1 is 2 y prime plus a0 is 2. And your f is x cubed. Okay, so this is in the Cauchy-Euler form from the definition of the Cauchy-Euler equation. So now what you do, without loss of generality, if you assume x, suppose your domain is in the positive real line, you introduce this change of variable, use the formula we have described, then this ODE will transform to this constant coefficient linear ODE. Right, x cube will become e power 3s. Now this is a constant coefficient linear ODE with right hand side e power 3s. You could very well use your method of undetermined coefficients. So if you look at the if you look at the characteristic equation corresponding to this ODE, you get a second order ODE with roots 1 and 2. So the corresponding complementary function is a linear combination of e power 1s and e power 2s, which is this. So now we can use the method of undetermined coefficient. You can also use the method of variation of parameter. Okay, so since the right hand side is of the form e power 3s, now you look for a particular integral as a times e power 3s, right? Because for this the annihilator is d minus 3, and if the solution of that, the root of that will be 3, so you have a times e power 3s. So use that information, right? So you just have to use this yp in this differential equation, substitute and see what happens. That is how you compute a. So if you use that, using it in the ODE of s variable, you get this equation which is going to give you that a is half, and therefore your particular integral is half e power 3s. So your general solution is the sum of the particular integral plus the complementary function. So this is so you see you have now solved a variable equation which is in the Cauchy-Euler form. Okay, let's look at and anyway, so this I forgot to mention. So this you have solved in the y and s variable, whereas the original equation was given in the x and y variable. So if you rewrite them in the x and y variable, you get the solution for the xy equation. Okay. Now let's look at other examples. So same problem one could have done using the method of variation of parameter. So I want you to do it as an exercise. I will just highlight just for recalling what you need to do. So Cauchy-Euler form, use this transformation to write it. Use this transformation to write it in the constant coefficient ODE form. Now earlier we used the method of undetermined coefficient. Now you use so you have two roots, so this is your complementary equation, there is no doubt about it. So in the x variable, the complementary equation is alpha 1 x alpha, right? You have used this, you have used x equal to e power s. So e power s is x, e power 2s is x square. So this is your complementary function for this equation, right? Now what you do is that you look for a particular integral by solving for v1 and v2, right? This is the method of variation of parameter. So this is a second order equation. Do as we said. So you find v1 and v2 by solving the matrix equation and add that, and then you can verify that you will get the same answer that we got on the previous slide. So I leave it as an exercise for you, right? So you can solve the same problem both with method of variation of parameter and also by the method of undetermined coefficients. Okay, now let's look at another example. So this is a cubic equation, and here again you see the coefficients are in the powers of x, so which means that it's a Cauchy-Euler form. So if you use this transformation s equal to log x, you get then you have this relation that x cube, right? If you substitute this transformation and compute all x in terms of s variable, then you are going to get a ODE in the s variable, which is this, where this 4 log x has become 4s. Now this is a constant coefficient linear ODE, third order ODE, where the right hand side is in the polynomial form, and this you can solve using method of undetermined coefficients. You can also use method of variation of parameter, whichever is convenient for you. So the complementary function is, so if you solve for the corresponding homogeneous equation, you will get a cubic equation. If when you solve for it, you get roots 1, 2 and 4, and that gives you this complementary equations. Okay, so once you have that, now you are looking for, now if you want to use method of undetermined coefficients, you are looking for a particular integral. You already see that here it's s, so the annihilator of this is 4 times d, right? 4 times d square, right? 4 times d square. So what is the root of corresponding root? So the root is 0, but 0 with multiplicity 2, right? Because it's a d square. So 0 with multiplicity 2, right? So which means it's e power 0x, which is 1. But since it's multiplicity 2, you need to choose a corresponding linearly independent function. So the one that is linearly independent to 1 is s, 1s. So that's what we have done here. So yp is as plus b. So you need to determine a and b. So if you differentiate this, you get yp is a. If you differentiate twice, you get yp double prime is actually 0, and yp triple prime is also 0. So if you substitute in this equation, what you get is 14a, 8as, 8b, 4s, right? In this equation, because you are doing this in the s variable, so you do it in this equation, right? So this is 0, second derivative is 0, so 14a minus 8 as, because yp is as plus b, so 8as minus 8b equal to 4s. Okay, So here you see the coefficient of S is 4, coefficient of S is minus 8a. So minus 8a is 4, which gives you, and 14a is 8b, so which gives you a is minus half, and second equation gives you b is minus 7 by 8. Thus the general solution in S variable is ys, right? So you have solved for this, so you add ys and yp and yc. That's your general solution. And if you write it in the x variable, you have this one. You have the general solution in x and y variable. Okay, so with that we complete this lecture. So in this lecture we have introduced the method of variation of parameter, right? And then we have shown that an ODE of Cauchy-Euler form can also be solved, can also be reduced by a transformation to a constant coefficient ODE, and can be solved via the method of undetermined coefficients or method of variation of parameters. Okay, so with that we end this lecture. I'll see you in the next lecture. Thanks a lot. Bye.